Hi, this is Jordan Hankin. This is my CE849 final project presentation on the evaluation of driveway assistance devices at low volume access points within one-lane two-way work zones. Here is a quick overview, but let's get right into it. So this is the driveway assistance device. It was introduced for use at low volume access points like residential, commercial driveways, and rural intersections on one-lane two-way work zones. It works in conjunction with portable traffic control signals and allows for the removal of flaggers. As you can see, there's a variety of designs, the horizontal, blank out, and doghouse devices, so there's a lack of standardization nationwide, and as such, a lack of research. So this is how the DAD works. Essentially, it cycles to an arrow to allow the exit point to proceed prior to a mainline platoon. It will cycle back to a solid red to hold the access point, and then will cycle to the right to allow the access point to continue before the mainline platoon. It's worth noting that in our study, the arrows were red. So quick lit review. Essentially the two studies I considered were from TxDOT and MDOT, which both showed high legal movement rates for the device and high safe movement rates. However, there were some issues noted such as site characteristics, volume at sites, signal timing, and overall comprehension of the device. So the objective of our study is to determine the DAD design which best conveys a legal safe movement to a motorist and develop guidelines for the DAD design and use that's best, and this is done through investigating these auxiliary signs. So our data for this project comes from a field data study at 10 driveways and intersections at a work zone in Benzonia, Michigan. We were interested in these 5 different signs, including the standard MDOT sign and these 4 alternative innovative signs. It's interesting to note that they all had this no turn on red sign, which was indicated to be important in a motorist survey. And again, these wait messages were also considered to be important in a motorist survey prior to the field data study. So we collected data at 10 different sites, but for this project I'm going to focus on McDonald's, which had our highest volume as well as all 5 signs tested. So real quick, we're interested in legal safe movements, which are a right turn on a right arrow or a left turn on a left arrow. Anything else is an improper movement. So the device experiences very high safe movement rates, as you can see by this chart. Looking at legal movements by sign type, overall 62% average. The 2 highest were the wait signs. Interestingly, those were indicated to be best comprehended in that motorist survey. So doing a quick ANOVA on legality by sign type, the 2 wait signs had the overall highest differences in legal movement rates. Interestingly, wait turn only had 2 significant higher differences. Interestingly, this one is significantly higher than turn only, which is without that wait message. So we decided to focus on the McDonald's due to the high volumes, the fact that the legal rates by sign were fairly similar to the overall rate, and the fact that there was a lot of noise between sites that we weren't sure that we could control for at this point. So I worked on building 2 different binomial logit models, one for legality and one for safety. This is the generic logit model with beta coefficients, x variables, and an epsilon random error term. I'm going to also provide some probabilities which were determined by holding variables at their average value. So for a categorical variable that is 0.5 and continuous was just the average value. So let's get into the legality model. As you can see here, 2 signs are statistically significant, both of which have that wait message. The wait turn only corresponds to a 85.5% probability of being legal, and wait for arrow is 86.6% probability, which is about 7 to 8% higher than the baseline proceed sign. Higher queue positions, less likely to be legal. The DAD display when a vehicle arrived at the driveway was important. So a solid signal display corresponded to about a 40% probability of legal movement, where left and right arrows corresponded to about 80 to 90% probability. If a vehicle joined a platoon, they were significantly less likely to be illegal, and turning right, interestingly, was significantly more likely to be legal. So queue time was the time spent in a queue prior to entering. Dwell time was time spent at the front of the queue, and gap time was the accepted gap. Gap time was significant and contributed to a decrease in the odds of illegal movement. However, queue and dwell time as those increase, they increase the odds of a legal movement. So some model summary statistics. These were the best statistics that I received when I was building models, so this was where I determined the best model was at this point in time. So now to get into the binomial logit model for safety. As you can see here, now there's only one sign that is statistically significant, but that is the weight turn only sign, and that corresponds to a 98.5% probability of a safe movement. It's interesting that the worst odds of a safe movement are the turn only sign, but that still corresponds to a 92.8% probability of a safe movement, so that's still pretty good. Again, higher queue positions are less likely to be safe. Interestingly, the data display upon arrival is now not significant, but still follows the same increase in odds trend. But then if you look down here at the data display when a vehicle enters the main line, that decreases the odds of a safe movement when the data is showing an arrow upon entrance. If you look here still, joining a platoon, significantly less likely to be safe. Turning right, significantly more likely to be safe. I think in both models, so both the safety and legality model, it's interesting to note that the direction variable may be capturing some site characteristics that are omitted from these models at this point. Now, going down to the time variables, now all three of them are positive, meaning that as any of these times increase, they increase the probability of a safe movement. I think it's interesting to note that gap time switched to a positive coefficient and is now not statistically significant, but in the safety model now, dwell time is statistically significant. So some model summary again. This model wasn't particularly predicting well the unsafe movements, and this could be indicated by the lower R-squareds, which mean that the model is not necessarily as well fit to the data. So in summary, for the legal model, both of the wait signs, longer queue times, longer dwell times, and arriving on an arrow signal contribute to better odds of a legal movement. However, longer gap times, higher queue positions, and joining a platoon have worse odds of a legal movement. In terms of the safety model, longer times and the wait turn only sign and the proceed sign have better odds of the safe movements. Worse odds come from the three other signs: higher queue positions, entering on an arrow, and joining a platoon. Some notes to consider are that the safety model had poor predictions, and then in both cases, neither model considered site characteristics or driver characteristics, which are certainly significant aspects of interactions with the DAD. However, in conclusion, the device does operate effectively at higher volume locations with high safe movement rates and a decent legality compliance rate. The lower legality compliance rate compared to the literature is probably due to the higher volume at this work zone and at the sites considered. Given the significance of the variables, it's clear that the weight message is an important aspect of a vehicle's interaction with the DAD. It improves legal and safe probabilities, so either of these signs, but especially the wait turn only sign. Again, given the statistical significance, the time spent at the DAD affects the movement, so that queue, dwell, and gap time. So this probably indicates that the DAD needs to ensure adequate signal timing to ensure that the temptation of illegal and unsafe movements are deterred as much as possible. And again, given the negative coefficients of the queue variable, certainly queuing does affect interactions with the DAD, so it's going to be important to study further how the DAD operates at higher volume locations. Some next steps for this study are going to be investigating the survey data and comparing those with field data findings. In future model building, it's going to be imperative to incorporate site characteristics. This was a big gap in the literature that we were not able to address in this study, and there are clearly aspects of vehicles' interactions with DADs that are affected by variable site characteristics. And given the statistical significance of the weight signs in both models, there's clearly warrants for further testing and validation of the weight message on a sign, both with the current signs shown here and potential new alternative auxiliary signs that make use of the weight message. So here are a couple of references. And thank you. Looking forward to questions and comments. And Dr. Savalainen, thank you for this course, and I look forward to hearing more. Thanks.